Okay, here I just, for completeness, discuss how you, what mathematical manipulation you need to do in order to change the left-hand side here to the material derivative. So we consider these two terms here independently, and so you have the time, the partial of the field rho times the field u. And here you know how you differentiate a product. So this is simply partial rho partial t times u. This field here just corresponds to the time derivative of the density times u plus rho times partial t partial u. Sorry, I meant partial u partial t. Okay, so this is the standard differentiation of a product. Now let's look at the second term. That one is a little bit more tricky. So you're looking at the divergence of rho u u. And what I'm going to do here is I'm going to write it as the divergence of rho u u. And this is simply to show you that this is really just the divergence of a dyadic product between the vector field u and the vector field, which is the density times u. This is still here a vector field. It's just the momentum field, if you want. Now this divergence here is a differential operator. It's a spatial differential operator. And of course, it's not just a derivative, but you have also, mathematically, you have similar differentiation rules as you would have if you had, just like here, if you had a simple derivative. Okay, so it so happens that you can find this formula in your book. The divergence of a dyadic product, so the divergence of a field A outer product field B, is going to look a little bit like the derivative of A times B plus A times the derivative of B. It will actually be the divergence of A times B plus A, the operator A grad B. So this term looks a bit like the derivative of A times B plus A times the derivative of B. It's not exactly that, but it is close enough. So if we use this first result from tensor analysis, then we can rewrite that here as the divergence of rho u times u, the divergence of rho u times u plus rho u grad u. And then we can use a second mathematical formula to simplify this divergence here, right? Because the divergence of a scalar field times a vector field is equal to the scalar field alpha times the divergence of A plus A grad alpha. Okay, so if I change this, then I obtain and that's time u plus rho u grad u. So now if I look at the left hand side, which is 1 plus 2, this yields partial rho partial t times u plus rho partial u partial t plus rho times the divergence of u times u. This here is a scalar plus u grad rho u plus rho u grad u. And so here we see that we have the vector field u, the vector field u, the vector field u. We can factorize the vector field u and write partial rho partial t plus u grad rho plus here rho times the divergence of u. All of this is a scalar, this is a scalar, this is a scalar, times u. And then I have left this term and that term, plus rho times partial u partial t plus u grad u. But this term here is the material derivative of u. This time here is the material derivative of rho. So this is the material derivative of rho plus rho divergence of u, and from the continuity equation this has to be equal to 0. This is equal to 0 from the this is the continuity equation. So you see that the left hand side, the left hand side here really reduces to rho times the material derivative of u, and therefore we can rewrite this as rho times the material derivative of u is equal to the right hand side, so the divergence of the stress tensor plus f.